In this video, I'm going to talk about ionic product of water, right? And if this is your first time visiting my channel or coming across my video, don't forget to like, share, and make sure you subscribe. It's very, very important. And at the same time, you can do it to check the playlist out. I've actually talked about the acid-base concept, but in this video, I'm going to be focusing on ionic product of water, right? Now, one thing I want you guys to understand is that we all know that water, which is actually symbolized as H2O, right, actually have the ability to react with itself. That is, it has the ability to undergo what is refers to as auto-ionization reaction. That is the ability for ionic molecule to react with each other, right? And in that scenario, we simply say water is actually amphoteric in nature. Water is an amphoteric substances, and the reason why is that, let's say we have two molecules of water, which is the first one, that's H2O, then it's reacting with the second one, which is also what, H2O, right? This gives us let's simply say we have hydrogen ion here, H3O plus plus what, OH minus. Now if you look at this down, we have a molecule of water here, right? Then we also have another molecule of water here, which is the one that you are seeing here. Now in this scenario, water is actually reacting with each other, right? And in that case, one is donating what, a proton, which is hydrogen ion, to another one, and the other one is what, is accepting a proton, right, to form hydronium ion and also what, hydroxide ion respectively. And in that scenario, we simply say water undergo auto-ionization reaction, which is what you are seeing here. Now what is auto-ionization reaction? Auto-ionization reaction is the ability of ionic molecule to react with each other, right? Thereby one is going to be donating a proton and the other is going to be accepting a proton. And in the case of water, water is an amphoteric molecule because it has the ability to behave as what, as an acid, and also what, ability to behave as what, as a base, right? That is, water can donate a proton and also water can what, accept a proton. And in that scenario, we simply say water is an amphoteric substances. Then I'm going to write some equation out to actually demonstrate the what, the properties of water when it is accepting a proton and when it is what, is donating a proton. Now suppose we have let's simply say we have an acid. Let's say we have weak acid HA, or basically let me just use hydrochloric acid that we are all familiar with. Then let's say we are reacting hydrochloric acid with water here. Look at this, right? So this is in its liquid form, and at the same time this is also in its liquid form. Then this actually react together to produce, here we are having H3O plus, which is hydronium ion, is in its aqueous state, right? Plus what again, we have what, chlorine ion, which is also in what, in its aqueous state. Now if you look at this very well, right, look at this very well, this actually what, an acid here, right? And what this acid is basically doing is that it donates a proton to water, right? And in that case, if this acid, which is hydrochloric acid, is dissolved in water, it's going to split into two. We're going to have what, H plus and also what, plus Cl minus. But because this H plus cannot exist freely inside what, inside water, right, that shows that we manage to react with water by forming hydrogen bond with water. And once it's formed hydrogen bond with water, a complex is formed, which is referred to as hydronium ion, right? It's actually the complex that is formed, because in the structure of water we actually have what, H with partial charge here connected to what, to oxygen here, which is carrying what, a lone pair. Then we also have another one attached to it, which is also carrying what, partial charge. Then this as well also has partial negative charge here. But one thing I want you guys to understand is that water is actually what, an aqueous molecule. What am I aqueous molecule is that it has charges in its structure, and due to what, to these charges that you are seeing here, it actually enables water to be able to form hydrogen bond with other molecule, like what, like sugar, right? Molecules like sugar, right? And molecules like what, like salt, right? So due to the let me simply say the ionic state of water can form what, hydrogen bond with this molecule that I just write out, the sugar, the salt, and also some metals at the same time. But let's just come back to what we are talking about now. Once this acid is being dissolved in the water, it's going to split, that is, it will dissociate completely in the sense that it is what, it is a strong acid, right? It's a strong acid, and we know that strong acid ionize completely in water. So in that scenario, that shows that once it splits, it's going to split into into hydrogen ion, as you can see here, and also chlorine ion, as you can see here. But this hydrogen ion cannot exist freely in an aqueous state, so it has to react with water and form this hydrogen ion that you're seeing here, right? So in that case, according to the definition of acid donates, right? Acid donates what? Donates a proton. That's actually what the definition, according to what Bronsted to Lowry concept. It says acid donates what? A proton, while a base accepts a proton. So in that scenario, this is the acid, and it is very strong acid because it ionizes completely in water. It dissociates completely in water, and that shows that it is a very strong acid. Now look at this case of this water. Water is behaving as a base here because it accepts a proton from this acid that you're seeing, from this hydrochloric acid. So since it's going to accept a proton from hydrochloric acid, that shows that it is a base, right? So that simply says it is a base. A base are substances, let me simply say bases are substances that tends to accept a proton, right? So once they accept a proton, they are going to form conjugate acid, and that is what you are saying here, right? So that's just it. So I don't want to delve into this conjugate acid and so conjugate base for now. I'm going to make that in a separate video. Now let's just come back here. We have hydrochloric acid and so and also this water. So water is acting as a base here, while this acid is actually a strong acid. But the strength of this acid is determined by the ability of hydrochloric acid to be able to donate a proton to water. Since it donates a proton completely, that shows that it is a strong acid, right? So that's just the first scenario I'm going to demonstrate. Now let's say we have another second scenario that we have here. Let's say we have the case where water is behaving like a base, actually like an acid rather. Now let's say we have the case of ammonia, right? Ammonia, right? Then we react it with water, which is H2O, right? This is going to give us what? Now let's come down and look at this. Now in this case, ammonia actually have a lone pair electron. And one thing about water is that water doesn't have a lone pair electron. It just carry a partial charges, right? Now one thing is that ammonia is going to accept a proton from water, right? And in that scenario, that shows that water is going to be behaving like an acid here, right? And ammonia is a base here. And the reason ammonia is a base is because ammonia, according to the definition of base, a base will accept hydrogen ion. That is it, a proton. So ammonia will accept hydrogen ion from water and form NH4 plus, which is ammonium ion, right? Then we are going to have the remnant of this water, which is actually hydroxide ion, as you can see here. So that's that water is donating a proton to ammonia to form ammonium ion and also hydroxide ion, as you can see in this case. And in that scenario, that shows that water is behaving as an acid, and in this case, water is behaving as a base, right? So due to the ability of water to be able to behave as an acid and a base, that is actually the reason why water is amphoteric in nature. It has two properties. It has the property of acid, and at the same time, it has property of a base. It can act as an acid, which is a proton donor, or as a base, which is proton acceptor. Hope you guys are following me. And that's actually what gives rise to the ability of water to be able to react with each other, which is actually referred to as auto-ionization. Auto simply means self. Auto means self, right? Ionization simply means the reaction that occur between ions, between ionic molecule. That is ionization. So auto-ionization, self-ionization, self-reaction. That is, water is reacting with each other, right? So let's basically bring out the reaction of water. Now look at this. Let's say we have two water molecules here, right? We have H2O here, right? This H2O is a water, right? Is in its liquid state. Then plus another molecules of water, which is also H2O, which is also in liquid state. This kind of reaction will always exist in an equilibrium manner, right? Because it exists in an equilibrium manner, right? So in that case, one is going to donate the proton, and we're going to have H3O plus, which is a complex hydronium ion in its aqueous state, and plus let me simply say another one, which is going to be hydroxide ion, right? Yeah, hydroxide ion is also in its aqueous state. Now this is actually a reaction that occurs between two water molecules. And what type of reaction is this? Is actually auto-ionization reaction. The reaction is referred to as auto-ionization reaction. Make sure you keep that in mind. auto-ionization reaction. Then one thing I want you guys to understand is that in order for us to, since we said this kind of reaction actually occur in what, in an equilibrium manner, right? So that shows that we need what, equilibrium constant, right, for this kind of reaction. And in that scenario, the equilibrium constant is referred to as what, as Ki, right? And this Ki is simply called what, the ionic constant. Ionic constant. And what is ionic constant used for? Ionic constant is used to calculate, let me simply say, to determine the ionic strength of water. Do you get it now? So we have Ki. Now, in order for us to get this Ki, we simply say, okay, let's just go ahead. We are going to have what, using equilibrium law, we are going to have Ki, which is what, ionic constant, is going to be equal to what, concentration of what, of the product, which is actually what, H3O plus, right? Then multiply what, hydroxide ion, which is OH what, minus. Then all divided by what, concentration what, of water molecule. And you know, this is actually what, 2 water molecule. That's going to be what, 2 molecules of what, of water, which is 2H2O. Then we're going to have this to what, to be H2O all raised power what, of 2, according to what, to let's equilibrium law. So we have product over what, of our reactant, right? So and we know that concentration of what, of water, concentration of what, of water, H2O, is actually what, is actually 55.56. 55.56. That's actually the concentration of what, of water. So now let's go ahead and put it here. You know, this is actually what, hydronium ion. It's actually what, let me see, the concentration of what, hydronium ion. If you go ahead and use what, and use pH, is actually what, 10 raised power what, minus 7, and that of hydroxide ion is actually what, that's 10 raised power what, minus 7. So to determine the Ki, which is actually what, the ionic constant of water, we're going to have it to be, you know, from here we can simply cross multiply here. So we're going to have Ki, right, then multiply what, H2O, right, all squared. This is going to be equal, we're going to have 10 raised power what, minus 7, multiply what, 10 raised power what, minus 7, right? In that case, now look at this. This Ki and also this water, concentration of water, is actually constant. So since it is constant, you can actually represent it as what, with another constant, right? So the other constant I'm going to represent it with is going to be Kw, right? So that's going to be what, let me simply say water constant. So and that's going to be what, Kw is going to be equal to 10 raised power minus 7 multiplied 10 raised power minus 7, and this is going to give us 10 raised power what, that's going to be 14. Right, so that's why that Kw is always equal to what, 10 raised power what, minus 14. So this is basically what the let me simply say the water constant is 10 raised power minus 14. Now, in order for us to get what this Ki itself, now what I'm going to be doing is that I'm going to have Ki to be equal 10 raised power minus 7, then multiply by 10 raised power what, minus 7. Then this is going to be divided by what, we are going to have concentration here. We're going to have 55.56 all squared. That's what we are going to have. And in that case, if we make use of calculator, let's see what we are going to have in this case, right? So pressing my calculator. So if I press my calculator, let's see what I'm going to have, right? That's what I'm going to have here. Now pressing the calculator, you're going to have Ki, right? We're going to have Ki to be approximately 3.24, right? Multiplied by 10 raised power what, minus 18. So this is basically what, the ionic constant of water. Ionic constant of water is actually what, is 3.24 multiplied by 10 raised power what, minus 18. So it's very, very important for you to know that. So this is just the ionic constant of water. Now let's move to the deviation constant of water. It's also very important, right? So let's move to the deviation constant of water. Now, in the case of deviation constant of water, we're going to have a water molecule. You know, that one is actually used to demonstrate the process in which water is going to use to react with another molecule. Now, suppose we have a molecule of water here, which is actually what, H2O, right? So whenever water dissociates in an equilibrium manner, we are going to have this word to be H plus, right, plus what, OH what, minus. Now, if you want to get what the let me simply say deviation constant for what, for this scenario, deviation constant is going to be what, is going to be Kd, right, and this is going to be equals to what, concentration of what, of H plus, right, multiply that of what, of OH minus, right, divided by what, divided by H2O, and H2O, concentration of H2O is actually what, 55.56. So that's what I'm going to have here. That's H2O, right? So we all know that concentration of what, of hydrogen ion is actually what, 10 raised power what, minus 7. Concentration of what, of hydroxide ion is also what, 10 raised power what, minus 7, right? So, and we know that concentration of what, of water is actually what, is actually 55.56. It is constant. It's actually constant. 55.56 more per the MQ. Now putting it into what, into this formula here, you're going to have Kd to be equal, here is going to be 10 raised to the power minus 7 multiplied by 10 raised to the power minus 7, right? This is going to be divided by what? 55.56. So that's what we're going to have. Now let me simply press this on calculator. Let's see what we're going to have. Right? That's what we're going to have. So this is going to give us 1.8, then multiplied by what? 10 raised to the power minus 16. So I want you guys to keep this in mind. This is 1.8 multiplied by 10 raised to the power minus 16. It's actually what the dissociation constant of water. But the case of 3.2 multiplied by 10 raised to the power minus 18 is actually the ionic constant of water. So there are differences. There are two differences between this. This is ionic constant of water, while this is what dissociation constant of water. Dissociation constant of water is actually used to demonstrate the scenario whereby water was dissociate into a hydrogen ion and also what hydroxide ion. But in the case of let me simply say ionic constant, is actually used to demonstrate a situation whereby water is reacting with each other. So whenever water is reacting with each other, we are going to have ionic constant, and that is referred to as auto-ionization reaction, which is simply called the self-reaction of water. Right? Hope you guys understand it, and I hope you love this video. So if you love it, make sure you give it a thumbs up, and don't forget to share it as well. Thanks for watching.